Hello everyone, welcome to eSpace. I am Chandran. This is the second part of sequence circuit analysis in this lecture. In this lecture, we will be talking about counters, asynchronous counters, synchronous counters, ring counter, and Johnson counter. So let us look upon what are counters. Counters are sequential logic circuits which can be used to count up or down a physical event. So in a digital circuit, the physical event is here is clock pulse. If so, suppose if we give a clock pulse to a counter, it in the up mode it will be counting from lower value to upper value. For example, from 0, 1, 2, 3, 4, 5, 6, 7, and again to 0. It goes in a loop. So I suppose if it is in the down mode, it will be counting from 7, 6, 5, 4, 3, 2, 1, 0, and again to 7. Again in a loop. And counters can be realized using flip-flops. So there are two types of counters, asynchronous counters and synchronous counters. In an asynchronous counter, clock is given to a single flip-flop and the output of that flip-flop is taken and next given to the second flip-flop. So it is in a cascaded state. Cascaded stage. The flip-flops will be cascaded to each other to realize the asynchronous counter. In a synchronous counter, clock is given to all the flip-flops simultaneously, and with a combination logic, it will be counting from 0, 1, 2, 3 like that. So let us start with single bit counter. It is also called mode 2 asynchronous counter. Here the counter is asynchronous. First you will look upon asynchronous counters. Why it is called mode 2 means it's the number of states of the counter. It is counting from 0, 1. Here you can see in the state table it is counting from 0, 1, 0, 1 like that. So there are two states in the counter. So it is called mode 2 asynchronous counter. And it uses a single flip-flop as we see in the logic diagram here. It is also called divide by 2 counter means the frequency of the output, that is at the Q0, the frequency is half, or otherwise the time period is double the clock, or the frequency is divided by 2 of the clock. So that's why it is called divide by 2 counter. And here is again, as we had discussed, it counts up to binary 2. So it is called mode 2 counter. So here are the waveforms. This is the clock input at the JK flip-flop, and this is the output Q0. So here we can see this is the frequency of the clock. The frequency of the clock you can see here, the Q0 is a frequency is half of the clock. That's why it is called divide by 2, or the time period is double. Frequency is half or time period is double. So that's why it is called divide by 2 counter. So now let us see a 2-bit counter. It is also called mode 4 asynchronous counter. Why it is called mode 4 means there are 4 states counting from 0 to 3. So first is 0, 1, 2 and 3. So there are totally 4 states. Again from 3 it again goes to 0. So there are only 4 states. So it counts from 0 to 3, so called as mode 4 counter. Also divide by 2 and divide by 4. Here at the Q0 output we will get the divide by 2, clock divide by 2 waveform, or the frequency is half of the clock, and here at Q1 you will get the 1 by 4th of the clock. So here we can have a formula here. The number of counter states is 2 raised to n. Suppose there are in a asynchronous counter there are 2 flip-flops like this, as we cascaded here. The number of counter states will be 2 raised to n. So here there are 2 flip-flops. So the number of counter states is 2 raised to 2, that is 4. So here are the waveforms. This is the clock pulse, and at Q0 it is divided by 2, frequency divided by 2, frequency half of the clock, and here at Q1 it is 1 by 4th of the clock. So here at combined Q0 and Q1 we will have the counter states here, that is 0, 1, 2, 3 and next then to 0, again to 0. So it will be going through a loop. So it will be counting from 0, 1, 2, 3, 0, 1, 2, 3 like that. So this is mode 16 asynchronous counter. Why it is called mode 16? There are, here you can see there are 4 flip-flops. So number of counter states is 2 raised to 4, that is 16. It counts from 0 to 15, so it's called as mode 16 counter. It counts from 0 to 15. So also called as also divided by 16 counter, because at the Q3 output we will get the 1 by 16th of the clock. Waveform frequency 1 by 16th of the input clock. So again here it is in the JK flip-flop, it is in the toggle mode because J and K are tied to 1, logic 1. So it will be in the toggle mode. Whatever previous value, suppose the previous binary value is 0, the next value will be 1, and accordingly when we cascade each flip-flop to each other, so we will get the half of the waveform of the previous flip-flop. So these are the state table. So it counts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then to 0. So it goes through a loop like 0, 1, 2, 3 and up to 15 and then to 0. And these are the waveforms. So combined we can see it is 0 to 15. Again we can see here the waveforms at the LSP. It is the half of the clock. And again at the Q1 it will be again 1 by 4, and here 1 by 8, and finally 1 by 16. So here this is a different counter. This mode 10 counter, that is decade up, asynchronous decade up asynchronous counter. Why it is called decade? It counts from 0 to 9, so called as mode 10 counter or decade up asynchronous counter. It is asynchronous type. The clock is not given to all the flip-flop simultaneously, because it is, as we earlier saw, the flip-flops are cascaded to each other. And let us see the state table. You will be getting much more clear view. It counts from 0 to 9, and after 9 it counts to the count value will be 10. For a 10, the binary value is this 1010, and we can, this is the special stage with Q3 equal to 1 and Q1 equal to 1, and we give the input to a NAND gate, and the NAND gate output is given to asynchronous clear of the flip-flop, and the clearing takes place asynchronously. That means that it does not depend upon the clock. When we get the value here, it suddenly clears all the flip-flops. So this is a reset condition Q3 Q1 bar, that is NAND operation of Q3 and Q1. So when it just reaches 1010, it suddenly clears, and next state will be 0000. So this is a state table. It goes on counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when it reaches 1010, it suddenly clears, and the next state will be 0000. And that's the logic behind the asynchronous count mode 10 asynchronous counter. So let us see now mode 16 down asynchronous counter. So here there's a little bit difference than the mode 16 up asynchronous counter. So again it counts from 15 to 0, so called as mode 16 down counter. Here the second flip-flop clock input is taken from Q bar of the previous flip-flop. So you can see here the clock input is of the Q bar of the previous flip-flop. So again in the same logic it is cascaded to each other. So it counts from 1111, and then it comes to 15, that is 15, 0, 15, 14, 13, 12, like up to 0, and then again to 15. So we'll be seeing the state table. So this is the state table. First value is 1111, and next to 1110, and this is actually E, D, C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and again next to F, that is a hex value F. So let us now see mode 10 down asynchronous counter. This is asynchronous type. It counts from 15 to 6, so called as mode 10 down counter. There are 10 states for the clock, for the counter. So it is called mode 10 down counter. So what happens is it counts from 15, then 14, 13, 12, 11, 10, 9, 8, 7, 6, and then when it goes to 5, it suddenly get preset. that is when it goes to preset condition, the value will be 1111. So after 6 it will be counting to f, that is all also, otherwise it will be counting to 15, f in hex and 15 in decimal value. So the preset condition is q3 plus q1. So we are given an OR gate, and this will be presetting all the flip flop, and the value will be 1111. So you can see first value is 1111, and then it counts to 14, 13, 12, 11, 10, 9, 8, 7, 6, and then it goes to preset, and then it counts to 15, that is 1111. So again, let us see another counter, that is mode 8 asynchronous counter with control input. The type is asynchronous. It counts from 0 to 7 when m is equal. There's an input here. Another logic input is additionally added here. So it counts from 0 to 7 when m is equal to 0, and from 7 to 0 when m is equal to 1. So here we have designed it. So here you can see what's the logic behind the up and down counters. For a up counter, the Q of the first flip flop is connected to clock of the other. So suppose when m is equal to 0, there are two as you can see a XOR gate here. When m is equal to 0, the value will be Q will be passing to the clock, and when m is equal to 1, the value will be Q bar at the output of XOR gate. So Q bar will be applied to the clock input. So that's only logic. So when m is equal to 0, Q is connected to clock. Again here Q1 is connected to clock of Q2, clock of third flip flop. So here when m is equal to 1, Q bar, the output of the XOR gate will be Q bar, and the clock input will be Q bar. Again here also Q1 will be Q bar, Q1 bar will be given to clock input. So it will be counting down. If Q is given to clock input, it will be counting up. So that's the logic behind here. So here we can see MQ, when m is equal to 0, Q clock m, that is a clock to the next flip flop input, it will be 0 1, same logic, not inverted, it will be non-inverted. And when m is equal to 1, the output clock m will be inverted, that is it will be Q bar. And you can see that state table 0, when m is equal to 0, it will be counting from 0 to 7, and when clock m is equal to 1, it will be counting from 7 to 0. So let us now see mode 16 synchronous up counter. Earlier in asynchronous type counter, we have designed with an intuition of just inverting like that, inversion logic like that. Suppose it is down, we will be connecting the Q bar of the previous flip flop, and if you want to count up, we will be connecting Q of the previous flip flop. But here it is, the design is different. There is a design procedure for synchronous counters, and first you have to draw the state diagram. That is S0, S1. Here we are taken mode 16, so there are 16 counter states. So it is count from S0 to S15, goes in a proper manner, and this is the block diagram of the synchronous counter. Here again we will be using the same flip flops. Suppose you can use any type of flip flop, D, JK or T, but here we will be using JK flip flop because it is that circuit will be much more simpler. So there are flip flops here, and this is next state logic is a combination logic circuit which gives the flip flop inputs from the counter states. From the counter states derives the flip flop input logic, and with that logic the flip flops understands what to give the next state of the counter. So that's why it is called next state logic here, and the next state logic is given to flip flop. Then the flip flop understands what is the next state of the counter. So this is a state table. We have to draw like this. We have to draw a state table like this, where there's a clock here, and for each clock there will be a present state and next state, and we will derive the flip-flop inputs from according to the present state to next state logic. So in the previous lecture, in the part 1 lecture, we have already discussed what will be the input for the state transitions. Suppose for 0 to 1, changing from Q0, you can see Q0 here, Q0 changing from 0 to 1, what will be the flip-flop input to the J0 K0 flip-flop? That is, what will be the input to the J0 K0 flip-flop? That is, suppose it is changing from 0 to 1, the input should be 1x. That is just like set, it can be 1 0 set condition, or it is a toggle condition, that is 1 1 or 1 0. So that will be 1x. And here you can see for Q1 to Q1, that is 0 to 0, it will be 0x. And for 1 to 0, it will be x1. And here you can see, here 1 to 1, it will be x1. So like that, we can have four combinations of flip-flop inputs where to decide what will be the next state of the flip-flop. So I have written according to the logic, I have written all the flip-flop inputs, and this is from 0 to 7, and we have 8 to 15. I have written all the flip-flop inputs. Now the next step is draw the K-map. Suppose this is the K-map for J0. We have got all 1, some don't care conditions. So suppose it will be J0 will be equal to 1. Again K0, we have got the K-map here. It is K0 equal to 1. And for J1, I written here. So here we will get Q0 and K1 also Q0. And J2 is Q1 Q0. So we have to put an AND gate here. And K2, again it is Q1 Q0. So again an AND gate. And here we will get Q2 Q1 Q0. Again an AND gate. You can cascade the previous AND gate to this AND gate. So these are the values in the. So we have derived the equation from the K-map for the next state logic. So this is the required circuit. According to the K-map output, I have written here. I have designed here the circuit. So here it is J0 K0 equal to 1, J1 K1 equal to Q0, and J2 K2 equal to Q1 Q0, and J3 K3 equal to Q2 Q1 Q0. So this is a required circuit. So if we follow the same procedure, we can design any type of counter according to this. And here you can see the clock is given to all the flip-flops simultaneously. So that's why it is a synchronous counter, synchronous mode 16 counter. So now let us see mode 16 synchronous down counter. So this is a state diagram. Here the counts from S15 to S0, that is 15, 14, 13 up to, it goes on, and 1 to 0 and again to 15. This is the state diagram. So this is the state table. I have written here 1 1 F2, this is 1 1 1 1 2 1, next value is 14, 15 to 14, and 14 to 13, 13 to 12, 12 to 11, 11 to 10, like that. So I have also written the flip-flop inputs according to the next state logic. These are the flip-flop input for this state transitions. Again it will be, and it is counting from 15 to 0. So this is a K-map. This is a value of J0 K1, J0 K0, J1 K1 is Q0 complement, and this Q1 bar Q0 bar. Again you can use an AND gate from the complement of the flip-flop outputs. So this you can see here I have put the J and K equal to 1, J0 K0 equal to 1, and J1 K1 equal to Q0, and J2 K2 Q0 bar and Q1 bar, and here it is Q2 bar, Q1 bar, Q0 bar given here. So this is a required circuit. Again, you can see clock is given to all the flip-flops simultaneously. So this is the design of the mode 16 down as synchronous counter. So we have studied all the counter logic. So there's a problem in a counter. Suppose we are using some fixed states for the counter, that is, if you are using for a three flip-flop, if you are using three flip-flops and the number of states is less than 2 raised to n, that is, here you can see the video example shows a design of mode 5 up self-starting counter. So if you are using 5 states, that is S0, S1, S2, S3, S4, and they gain to 0, there are 3 unallowed states. Suppose if the counter, suppose with a noise or glitch, if the counter goes to these 3 states, it has to come to the initial state or any of the states. So here this is called the lockout problem. Suppose the flip-flop lockout in a counter initial situation is the counter goes into an unavailable or unallowed states and remains there. So that is a lockout in a counter. So counter which avoids this problem are called self-starting. So what we will do is, in the state diagram we will be setting from, suppose it is there are 3 states S5, S6, S7. When it reaches there, we have to give to next state to S0. So that is the design. You can see here the S5, after when it goes to S5, it goes to S0. When it reaches S6, it goes to S0, and again when it reaches S7, it goes to S0. So this is a state table of mode 5 self-starting counter. So it counts from 0 to 1, 0, 1. Next state will be 1, and 1 to 2, 2 to 3, 3 to 4, and 4 then to 0. That is a normal sequence of the states, counter states. But here we are given additional states, that is, if it goes to 5, then next stage should be 0. And again here, if it goes to 6, the next stage should be 0. Again if it goes to 7, the next stage should be 0. So these are the flip-flop inputs according to the state transitions here. Here again we are using JK flip-flop. So this is J0, Q2 bar, K01, J1, Q2 bar, Q0, K1, Q0, but Q2, J2, Q1, Q0, K2, 1. So these are the 3 flip-flop, that is J0, J1, J0, K0, J1, K1, J2, K2, Q0, Q1, Q2. So this is a logic according to the K-map equations. You have designed the AND gate and OR gate according to the K-map values. So this is a required circuit. Again you can see clock is given to all the flip-flops simultaneously. So it is a synchronous counter. So here we will seeing a special type of counter, that is ring counter, and there are n number of flip-flops here taken 4 flip-flops, and here you can see it is a D flip-flop, not a JK. It is a D flip-flop, and clock is given to all the D flip-flops simultaneously, and the D input of first flip-flop or the LSB is taken from output of MSB, that is output of last flip-flop, and each output of each other flip-flop are given to D input of the next flip-flop. You can see here. So what happens is, suppose all the outputs are 0, 0, 0, 0, 0. We will be setting asynchronously Q0 to 1, and what happens is, in the next clock this 1 will be shifting to next flip-flop. So in the next state, suppose it is in the 1, 0, 0, 0, the next state will be 0, 1, 0, 0, and the next state, again the next clock pulse, it will be 0, 0, 1, 0, and next it will be 0, 0, 0, 1. So that what means that the 1 will be circulating through the others. Suppose if we glow a LED here, this LED will be glowing in a serial manner. That is it will be LED will be glowing at the first clock pulse here, and next clock pulse here, and next clock pulse here, and next clock pulse here. So it will be going, that each LED will be blinking in each clock pulse, that it will be circulating in serially. So for a n bit ring counter, it will be mod n. There are, suppose for a 4-bit ring counter, there will be 4 states. That will be mod. It will be mod 4. So we'll see the state table. So we'll get a better understanding if we look at the state table. So first clock is we are resetting the LSP flip flop. That is here it will be resetting, and the next clock it will be 0010, 0100, 100. So as I told earlier, the 1 will be circulating through all the flip flops. So again, this is the pattern. So to understand the pattern, this is the pattern. 1 will be circulating each other. And this is a timing diagram. So at the first clock, we asynchronously set the clock, set the flip flop in output. So this 1 will be circulating like this through all the flip flops. So this is the counter waveform. So you get a better understanding if you look at this, and this pattern is repeating infinitely. So next special type of counter is Johnson counter. So again, the only difference is that the D input of the first flip flop is connected to Q bar of the last flip flop. That is not, earlier it was in the ring counter it was Q, but here it is Q bar. So you'll get a better understanding when we see the state table. And for n with Johnson counter, the number of states is mod 2n. So suppose if you are having 4 flip flops, the states for Johnson counter is mod 2n, that is 2 into 4, that is 8 states. So this is a state table of the Johnson counter. So here there is no need of asynchronously clearing or asynchronously presetting or clearing the flip flop. Starts from 00 and then it goes to 001 because the Q3 bar is connected. That is Q3 bar, it is 1 is connected to Q0. 1 is connected to D0, so it will be 1, and this 1 will be passing like this. This is the pattern. So there are 8 such states, you can see here. So there are 8 states, and this is a timing diagram. See, you can see this big pulse will be traveling through the flip flops. So this is the pattern. You have to understand that in the ring counter there is only one clock pulse. That is, one clock pulse was traveling here, but here that is the width is 4 times the clock pulse. That is 1, 2, 3, 4. 4 times the clock pulse. So this is a pattern for Johnson counter. So that's it. We'll see the next topics in the next part, in part 3. Until then, goodbye, and please like and share the video and subscribe the channel. Thank you. If you have any doubts, you can mail me to chanch484@gmail.com, or you can put the comments at the comment section. Thank you.